Hey guys, back for another video lesson. I know it's not super exciting, but we really, like I've been telling you in class, we've got to keep moving here as we go. But we need jokes. So here we go. What's a pirate movie rated? Arg. I don't know if that was any good or not. Which superhero travels by public transportation? Which superhero travels by public transportation? Buzz Lightyear. That was so-so, right? This one isn't bad. Why are movie stars so cool? Because they have many fans. There you go. There's your jokes for today. Okay, we are back where we were, and we are definitely going down new problems. We're going to do a problem today that is definitely an AP problem, and there will be one just like this on the test. So let's pick up where we left off. We didn't quite complete the notes we were on on this page. So we were doing this, and we were writing these reactions, and we did all that. But then there was this question, and this reviews an acid and a base, and an acid is a proton acceptor. And there's two really definitions of acids and bases, but really there's one for acids, and it's always that right there is acids proton or give up an H. But bases have two definitions. They're this, what this says, a proton or an acid or an H plus acceptor, but they're also known for giving up OH. So going back to the equations we did above, letter A and letter C were kind of the older historical, that's called the Arrhenius definition of bases, where they give up OH. But in B and D, it's this last definition. So the question says, use these definitions, identify the acid and base for the last set of equations. Okay, so if I go back to this last equation, and the definitions, whoa, I almost fell down. That'll give you something to watch. I got hooked up in the cord there. But we took acetic acid plus NH3. Okay, and this is, we wrote the equation for this. And so this being an acid, this was the acid, and this was the base. And so this gave up an H, and this accepted an H. And so what we got off was C2H3O2 negative plus NH4 positive. And so to recognize these, to identify these, acids always start with an H. The bases could end in OH, but they also, if you have the whole reaction, if you look at base gains an H. So it goes from NH3 to NH4. So acids lose an H, and bases can do two things. They can either give up an OH, or like here, they can accept an H. And this is something that, depending on how far we get in the springtime, but we'll go way more into this, but we'll have a base, and the base always has a conjugate acid, and an acid has a conjugate base. So, okay, so that finishes that. Okay, now on to the next problem. And this problem is definitely, like I said, the rest of this chapter, we are now going into new stuff, AP chemistry stuff. Okay, so we have completed that slide. Okay, so here, and again, I keep saying this, but I'm working on the test now, and I always throw a problem like this on the test, and it's a hard problem, and there's at least one like this in the book, and that I'm hoping you guys will be working on those problems. Okay, so if you break this down, 28 mils, 0.25 molar H2SO4, and I'm going to write this all out, is reacted with 53 mils of a 0.320 molar KOH. Determine the grams of water that forms. Okay, now that is not an easy question, but that question probably could have been done in first year chem, a really, really hard problem in first year chem. But then the second part, calculate the molarity of all the ions left over. That we did not do in first year chem. So here we go. And this might be a question that you guys, as we go through this is going to take us a few minutes to do this problem. And you might look at this and go, okay, I need to go I need to ask Mr. Wood about this next week. And so here we go. Hopefully you can follow along. So many, many times, not only now, but in our class in general, where I'm going to start out, where I'm going to teach you guys, what I always do is I just write out the chemical reaction for what's going on. Write out the reaction if I can. And then number two, I get everything into moles. So those are kind of my steps. So if I write out the reaction here, I've got H2SO4 plus KOH. So I'm going to write out the reaction here. And this is an acid-base reaction. This is one that we could have done in first year chem. This is outers and inners, strong acid, strong base. So always going to give off water. Those are the outers. And then the inners is going to be KSO4. And just to make sure you're following through on this, if K is a 1 and SO4 is a 2, it's K2SO4. Okay, so there's the reaction. This is aqueous, and in acid base, this is a liquid, and this is going to be aqueous, and this is aqueous. Okay, and then I need to balance it, and to balance it here, I need 2 here, 2 here. I think that balances it. So 2 Ks, 1 S, 4 H's, 4 H's, 6 O's, 6 O's. So again, what I did there, acid base, strong acid, strong base, outers and inners. And again, practicing writing equations, which we'll do a whole bunch. Okay, so now this is what I always do. I have all these numbers, so I always write down the numbers that go with what part of the balanced equation. So I have 28 mils, and I have a 0.250 molarity of this, and I have 53 mils, and I have 0.320 molarity of this. Okay, so in the first question, again, this would have been a really hard problem in first year chem. And again, for last year, like I said last time, is in the spring, of course, with all that was going on with the virus, we didn't get to really in class do these problems. But we're trying to solve for grams of water. So I wrote out the reaction. This is a limiting reactant problem. Remember, I can find moles by doing molarity times liter. So I wrote out the reaction. I'm going to get everything into moles. So I've got moles of H2SO4. So I'm going to take the molarity. I'm going to get this into liters. And then I'm going to find moles of KOH. So I'm going to write out the equation, and now I'm going to get everything into moles. And I've got to get the milliliters into liters. So when you do this, you've got to get milliliters into liters. Okay, so I've got 0.25 times 0.028. So we get 0.007, get my sig figs right, moles of H2SO4. I have 0.00 or 0.010. 170 is what I go to moles of KOH. So I wrote out the reaction. I got all into moles. Now I got to figure out which is limiting, which runs out first. And this time I can't just look at moles because the coefficients up here is 1 to 2. So I use this up twice as fast as this. So what I always show my class is if you just take moles and divide by the coefficients, so H2SO4's coefficient is 1, and KOH's is 2, and I compare, and the one that is smaller is the one that is limiting. Okay, and that's all I do with this number is I just compare and figure out what's limiting. So if I look at these, the smaller one is the one that is limiting. So because this is smaller, this is limiting. So then to figure out the grams of water, I'm going to use the limiting reactant. So now I'm going to do stoichiometry. So look at this. You had to write an equation, had to use molarity to figure out moles, figure out what's limiting. And now, and I'm going to start with this. I don't really, all I'm going to do there is figure out which one's limiting. So now, and that 0.007 to 0.0085, that was just to figure out what's limiting. So now I'm going to start with the moles of H2SO4, and I'm going to go to moles of water. So the ratio here is 1 mole of H2SO4 for 2 moles of water. So I did mole to mole. And then for 1 mole of water, the molar mass is 18. Okay, so if I do the math, and again, this question in first year chem, probably a lot of you guys with some work could have done this. Okay, so there's the first answer. Again, there'll be one like this on our test. I can't remember if chapter 4 quiz has a problem like this or not. I know there's one like this in the book. Okay, but then what is new is the second part of this, and it says calculate the molarity of all the ions. So there's 4 ions. So I'm going to write out the net ionic equation. So to figure out the ions, I'm going to write this out. So I'm going to kind of be going back and forth here. I'll lower the screen a second. So again, I'm going to write out the CI, the complete ionic equation. So I'm going to take 2H positive plus, this is aqueous, plus SO4 negative 2. And again, this 2, because it's not part of a polyatomic ion, became a coefficient. But this 4, because it's part of sulfate, stayed as a subscript, okay? So here, in this case, the 2 goes to the K and the OH. So I have 2K plus 2OH. Again, what I'm doing is what I did in the last lesson. I write out complete ionic equation. I'm dissociating everything. But the water, I don't dissociate. Just like a precipitate, like the solid. Okay, and then this, 2K, and again, because that 2 is not part of a polyatomic ion, it goes to the front. Okay, so everything is dissociated. Now the point of the problem wasn't to go on to the net ionic equation. The question was to figure out, I'm going to move the screen down now, the angle here, was to figure out the molarity of all the ions. There's 4 ions. Well, if I go back, I know that I have 0.00700 moles of these 2 right here. And I have 0.0170 moles of these 2, and that came from right here. Okay, so I'm going to go back and do the dreaded ice table. Remember, initial change equilibrium, and that is something we'll talk about in the winter, spring is equilibrium. But just think of it as the start, the change, and what you end up with. That's what happens in an ice table. To me, this is the way, and a lot of times, especially we get into the winter and spring when we're doing equations, this process is very consistent, is that we write out the equation, we get into moles, and we use an ice table. Okay, so I know now you got to watch this. So there's 0.00700 moles of the H2SO4, but there's 2 H's. So I'm going to multiply this by 2. So I'll explain that one more time. So there is, if I go back up here, for the H2SO4, there was 0.007 moles of that, but there's 2 H's. So I took the 0.007 times 2, and that's where I got 0.0014, 0.007 times 2. But there wasn't 2 of these, so there's 0.007 of that. Now over here, now this 2, you go, okay, well then, because of this 2, I multiplied that by 2. But see, this 2 was from a subscript, which meant when it dissociated, there was 2 H's. This 2 is a coefficient, which simply is a mole ratio. So I am not going to multiply by 2 here. There's not, for every 1 KOH, there's 1 K and there's 1 OH. Okay, so those are moles of all those, okay? On this side, and I'm not really going to worry about water because we've already dealt with water. But the first thing I'm going to look at is the spectator ions, the K and the SO4. They didn't change at all. So because they're spectator ions, so they're going to end up with what they started with. So moles and moles. Because they're spectator ions, they weren't consumed at all. So what I started with, if I went over here, that's what I would have ended up with. But the key here is the H and the OH. And I'm not done yet. I'm not done with those two. I'm going to come back to those in a second. But I got to ask myself, okay, which of these two is limiting? Well, remember, we determined that the sulfuric acid was limiting. And if I look here, moles of this and moles of this, and the way I'm teaching you, the way I guess I always find it the easiest to figure out what's limiting, is to get it in moles and then to divide by the coefficient. And the one that's smaller is my answer. This is the one that's smaller, which means this one is completely consumed. We're using this same idea in terms of limiting on the lab, the gravimetric lab, what you guys just did, is that, remember, one of them you added and there was a color change, meaning there was an ion there, it was an excess. The other one was clear, which meant it was consumed. So here would have been 0.014, which means I would have had 0.003 left over. Okay, all that, okay, I'm going to change the screen now. Now to figure out the molarity of every ion. So what I've got H plus, so you can't see that, but I've got H, here are my four ions, or H plus, SO4, K, and OH. So now I'm just going to move the screen over to here. So if I analyze every ion, so H plus in the brackets mean concentration, and I've got SO4, and I've got K, and I've got OH. And remember, the brackets mean moles per liter. The brackets mean moles per liter. Okay, so if I go back, I'm going to make you dizzy here, but if I go back and forth, so I go over here, the H plus was 0. So here then, the H plus was consumed, so it'd be 0. And the volume, if you go back to the problem, remember for here, I want moles per liter, the overall volume. Well, here, I've got 28 mils plus 53 mils. So if I take 28 plus 53, that is 81 mils, which I want to get into liters. So the volume here, and in this case, it won't make any difference, but it'll be divided by 0.081. So where I got 0.081 was, again, I added up 28 plus 53. But the answer for the H plus is 0. None of that is left. Okay, for sulfate then, I come over here, and for sulfate, I have 0.007. Okay, so over here then, for sulfate, I'll take 0.007, that's the moles, divided by 0.081. So 0.007 divided by 0.081 gives me 0.086. And capital N for molarity. I guess I really should, I'm looking at this for my sig figs. I think should have 3, so 0.0864. Okay, for the K, so I go back over here, and so for K, these are the moles. I got 0.017, so I'm going to take 0.017, divide again by 0.081. The volume is always going to be the same. So here I get 0.210. And then for the OH, again, I go back here, and the OH is 0.003. Again, divided by 0.081. And that gives me 0.0370. Okay. That is a tough problem. That is a tough problem. That is a good chemistry problem for anybody that does chemistry. That's a good problem. Hey, Mr. Connors, I'm making a video, but go ahead. Got a question?
Yeah, there's pieces of metal there.
Yeah. Yeah, they are. Yeah, they are. Okay. So, and again, if you guys have questions on that in class, please feel free to ask. Okay, then. Okay, back to the notes. And I'll know who's not watching videos when we come to the first test, and you'll go, I don't know what you're talking about on a problem like that. Definitely need to try that problem. Just real fast. I always do these kind of for your informations, but this is the reaction. This is never going to be on a test or quiz, but this is when we start our car and run our car. But notice oxygen is a limiting reactant, causing side reactions that produce pollutants. In the 1990, because of these pollutants, the United States Congress passed the Clean Air Act to lower air pollution, go to get emissions tested. This required oil companies to add a substance to gasoline to prevent these side reactions. These additives needed to increase the amount of oxygen present. The choice was this MTBE, called oxygenated fuel. Increasing the oxygen present had a higher chance of complete combustion. But the immediate results were positive. However, over time, it began to appear in drinking waters. That wasn't good. So via gasoline spills and leaking from underground storage. So imparts a foul taste to water, a turpentine-like odor, and a suspected carcinogen. So the public response was, of course, swift and dramatic. Lawsuits were filed, and many states banned this MTBE. Now they use ethanol. Next time you get gas, you should look on the pump and see if you see that. And this is, again, to get gasoline to burn better. Okay, I want to talk about this slide, and then this is where we will stop. This is, if you remember, in first year chem, we did a titration, and we're going to do, a matter of fact, the lab that we're going to do, we're going to start another lab. We're going to do it's got two parts, and we're going to do the first part as a class, just to save time. We'll just get our data together. But it's going to be a titration. What we did in first year chem was a acid-base titration. What we're going to do in class is a reduction oxidation titration. But a titration is a lab technique used to determine the concentration of a substance. And you add a titrant from a burette to the analyte, the solution you're testing, and you measure the volumes of each solution at the equivalence point. And the equivalence point is where the moles of acid equal the moles of base. And we always use the indicator phenolphthalein. And again, if we get far enough in the spring, we're going to some of the things on this page we're going to come back to. But we'll look at different indicators. And you'll see why phenolphthalein is a good indicator. It changes color, and the reaction is used up. And the end point is when the indicator changes color. And for right now, we're going to say the end point and the equivalence point are the same. And again, if we get to a certain place in chapter, I think it's 14, it just depends on how far we get. We'll kind of review some of these terms. Okay, so let me just again kind of do a diagram here on reviewing what we did in first year chemistry. So what we did, and I bet if you guys were in front of me and I asked you guys, do you remember that? I bet a lot of you guys would remember that. So what we did is we had, just like the diagram showed us, we had the burette, and we had a flask. I'm lousy at drawing, and we added this here, and we had this down here, and we had the solution, and we were trying to figure out the concentration. I think we're trying to figure out the concentration of a base, but this is what we did, and this was the chemistry. We didn't really talk about this in first year chem, but what happens is the indicator, the phenolphthalein, is a weak base is really what it is. And when it's mixed with H plus, this reaction occurs. So this is the indicator, and this is clear or colorless. And this again, last year, we didn't have a chance to do this. And so I know in my class, I showed I think it was a lady from a university doing a demo on this. Again, this is something that hopefully we can do in the spring. And this is like a pinkish color. So when you add the base, you have phenolphthalein, or when you add phenolphthalein to the acid, it goes from pink to colorless. But then if you take this and now you mix it with a base, what happens is this. And so again, this is clear or colorless, and this is pinkish color. So what I'm trying to show you here is that we have this solution and we add an acid to it, it becomes clear or colorless. And if you took chemistry 2 years ago, and I know some of you did, we did do this, where it went from pink to colorless, and it was kind of cool to watch it go from one to another. So we add the acid, it becomes clear or colorless. But then when we take that solution and we add the base, so here's the base, and here was the acid, then it became pink. This is what happened in the titration that we did in first year chem. Now what we're saying, and right now, and again, this depends on how far we get, but the equivalence point is where the color change, or the equivalence point, get ahead of myself, is where the moles of acid equal the moles of base. That's what happens at the equivalence point. Everything is equal. And for right now, and the end point is technically where the color change occurs. And so if you have a family member or friend who's good at chemistry, they will know that really a good lab gets these two to be at the same point. And for us right now, we're just going to say they are. The equivalence point where the moles of acid equal the moles of the base, and where the color change occurs, these are the same thing. And when we get into springtime, we'll get a little pickier on that. But for right now, and again, who knows how far we're going to get in the springtime with the virus around. But the equivalence point and the end point are one and the same. The equivalence point are where moles of acid equal the moles of the base, and the end point is where a color change occurs. Okay, I think that is a good place to stop. Definitely covering some new ground, and we got some really good problems ahead of us. And we're going to be getting through everything before fall break and getting that first test done. So, guys, hey, have a good weekend, and I will see you guys next week. We'll finish that lab, and nothing's due Monday or Tuesday, but you can be working on those chapter 4 problems. Hey, talk to you next week.